Welcome everyone, and today I'm really delighted to introduce Robert Hoye. Robert carried out his PhD in Cambridge and spent a while at MIT developing his expertise in defect-tolerant materials. He returned to Cambridge and he won a Royal Academy of Engineering Fellowship, and actually I was his mentor while he was at Cambridge, and now I'm not allowed to be because in 2020, Robert moved to Imperial. In January, actually. So he had at least 2 months at Imperial before lockdown. and he recently, he led a very successful road mapping exercise in the area of photovoltaics with the IOP and the Institute of Manufacturing. And that was funded by Royce. Now, Robert's research is on defect-tolerant materials to enhance the performance of light harvesting. And incidentally, that also means indoor light harvesting. So today's talk is on bismuth-based materials and addresses band gap tuning, defect tolerance, and indoor light harvesting. So Robert, over to you.
All right, thank you, Neil, for the very kind introduction. And this is now the second LCN seminar I've given. The first time was, I think, almost exactly 2 years ago, and you also introduced me then. So it's good to be giving an LCN seminar again. And things have changed in the 2 years. Biggest change is probably I've moved to Imperial, and as Neil mentioned, I joined the Department of Materials as a lecturer in January 2020. So I'm very glad to be here to give another LCN seminar. The previous LCN seminar I gave was about bismuth oxyiodide for solar cells, and some of the key developments we made since then was in developing bismuth-based double perovskites and developing chemical-based strategies to tune the band gap. And a more recent work we did was to apply our bismuth-based photovoltaics, not just for outdoor solar cells, but also to harvest indoor light to power electronics, part of the Internet of Things. So I'll be talking to you about these recent developments that we made in my group. But first of all, I just wanted to introduce my group. So you can read all the details in my group website here. And broadly speaking, we work on 3 main areas. So we work on defect-tolerant semiconductors, and these are materials that can achieve low non-rate recombination rates despite high density of defects. And what that means is that you can make these materials using cost-effective, scalable, and low-temperature processing methods but still achieve high efficiencies. We also work on developing scalable manufacturing routes for new materials, particularly vapor and solution-based methods. And we work on applying these materials into devices. We particularly focus on solar cells and light-emitting diodes. But more recently, we broadened our application space, and we've collaborated with groups to work on photoelectrochemical cells as well. We also work on more advanced structures like tandem devices, and I collaborate with a group in Singapore on that effort. So at Imperial, my lectureship is associated and tied with the Royce at Imperial, and the theme is on atoms to devices. So my research is describes very well the theme of my research as well, which is going from the atoms, going from the design and discovery of materials, as well as their nanoscale characterization, all the way through to pushing forward these materials into device applications and thinking about what we need to do to commercialize these materials. So before I talk about the research, I just wanted to thank the people who were involved in the works I'll be sharing with you today. In particular, I'd like to thank my PhD students, Tamida Huck, Ziwei Li, and Rob Yacht. And these are the people who led most of the papers I'll be sharing with you today. I'd also like to thank Aaron Walsh, who's also a member of professor in the Department of Materials here at Imperial. And he and his colleague David Scallon, as well as the student Sean Cavana, did the calculations that I'll be talking to you about today. And I'd also like to thank Vincenzo Pecunia and his team at Suzhou University in China. And his team was the one I collaborated with for our recent work on indoor photovoltaics. And I'd also like to thank Mari and her team colleagues in Lead-Halide in Finland, who did the Rutherford backscattering spectrometry measurements. And I also like to thank the funding sources from my side, especially the Royal Academy of Engineering. So in the first LCN seminar I gave last time, I was talking about solar cells, and I think we all appreciate the importance of accelerating this renewable form of energy, and that was certainly one of the key themes of the materials for the energy transition roadmap that Neil mentioned earlier. Today, I also want to talk about IoT, and we need to, one thing we should appreciate is that in the very near future, many of the new consumers of energy will be small and autonomous devices, part of the Internet of Things. And by Internet of Things, we're talking about an ecosystem in which lots of small devices can communicate to make smart homes or smart healthcare, for example. And one example could be that you could be wearing some electronics in your clothing, or you could have a smartwatch, and this could communicate with receptors in your house, and that can then activate them to switch on the lights or to increase the temperature or to boil the water, for example. So making an interactive environment rather than just a static environment. And this is becoming much more widespread and much more common. And it's predicted that by 2025, we will have 75 billion devices part of the Internet of Things. And as I mentioned, many of these devices will be small and autonomous, and they'll be in remote areas. So, for example, if you have something on your ceiling, think about your smoke detector at home. That's on the ceiling, so you can't just connect that to the grid. You have to have a remote power supply for these autonomous devices. And maybe the first thing you think about would be to use a battery to power these devices, and that's certainly what's very commonly done. But the challenge with batteries is that they have a limited lifetime. These devices last for 5 to 20 years, whereas a battery will only last for maybe 1 year or maybe only a few months, depending on how much power you're drawing from the battery. So once you go beyond a certain number of devices part of IoT and a certain level of complexity, it's no longer practical to use the battery to power every single one of these devices. And some people predict that if we only use batteries as the remote power supply, we will limit 80% of the potential of IoT from being realized. So we need to have alternative power supplies. And one of those is to use solar cells to harvest the light that we have in our houses to power these indoor devices. And the good thing about solar cells is that these have a much longer lifetime, so they can last for 5 to 20 years. So they can last for the entire lifetime of the device itself. And these solar cells could harvest light to directly power these devices, or they could work in conjunction with a battery. So if any of you have used a calculator with a solar cell built in, you've already come across an indoor solar cell. That solar cell in the calculator, that's made from amorphous silicon. And this market has become, has come to life quite recently. It's a very fast-growing market, indoor PV. The annual compound growth rate is 70%, and that's a much higher growth rate than some of the other markets like wireless sensors, which is part of IoT, and also much faster growth than the outdoor PV market as well. And some people did some calculations to work out whether indoor PV could power some of the most common wireless sensors used in IoT. And you can see here that if we have 30% efficient solar cells indoors with a 10 centimeter squared area, we can power quite a large number of these. The problem with amorphous silicon is that the efficiencies aren't 30%. They're actually less than 10% for commercialized devices. And we have to bear in mind that amorphous silicon is quite a well-developed technology. And the reason why the efficiencies are relatively low is because we have a lot of defects. Once you go from a crystalline structure to amorphous structure, you have a lot of dangling bonds and a lot of defects, and that will limit the efficiencies. So the question is whether we can find alternative materials that can achieve much higher efficiencies than amorphous silicon, that can reach 30% efficiency or even higher. And that's something we'll be talking about today. So if we look at alternative materials for solar cells, this chart gives you a summary of some of the more important ones that have been developed for outdoor PV over the past few decades. And the most common material used for outdoor PV is crystalline silicon. That's represented by these blue squares that you see here. So this has been worked on for 60 years now, and after 60 years of development, the efficiencies have reached 26.7%, and that is very close to the outdoor efficiency limit for these materials. But silicon is not perfect, and there's a lot of limitations with silicon. And because of that, a lot of people have been working on alternative materials, which is summarized in this bottom right-hand corner here. So if we zoom into that, what you can see is that one of the fastest growing new technologies is represented by these yellow circles here, and these are the Lead-Halide perovskites. And we have to bear in mind that this has only been developed for 1 decade compared to 6 decades for silicon. And after just a decade, the efficiencies for outdoor PV for the perovskites have reached 25.5%. This is a little bit out of date. And that is more efficient than multicrystalline silicon. And these polycrystalline perovskites made at low temperatures are almost as efficient as the best single crystalline silicon solar cells. So that is really quite remarkable. And this shows you what these perovskites are. So that's a typical device structure. And here you can see the crystal structure for perovskite. In this case here, we have lead as the B site cation, and these are octahedrally coordinated with halides, and usually it's an iodide if we're using this for solar cells. And the advantage of this material is that you can process them from solution and grow them at 100 degrees Celsius and achieve devices as efficient, almost as efficient as the best silicon devices, which are processed at over 1,000 degrees Celsius. But the problem with the perovskites is that they contain lead, and lead is toxic, but it's also regulated as well. So if you want to sell a lead-based product in Europe, you have to abide by the Regulation of Hazardous Substances Directive. And this stipulates that you can only have up to 0.1 weight% lead in your device. But we can, we can work around based on the way this has been defined, and the device has been defined as based on a homogeneous layer. And you can argue that your homogeneous layer can include the substrate. So if you include a glass substrate with a perovskite solar cell, then actually the overall lead content falls below this 0.1 weight% limit. But if you're using perovskites for wearable electronics, for example, you don't really want to wear solar cells on glass. So you actually want to have a solar cell on a flexible substrate, such as PET, for example. And if you have a flexible plastic substrate in your device, then actually the lead content goes above this limit. Now for outdoor PV, there's an exemption against having to follow these rules. But for consumer electronics, for example, if you want to use solar cells indoors or embedded into your backpack, you're not exempt. You have to follow these regulations. And so the fact that you'll have lead that exceed these limits will be a problem for commercialization. And we also need to bear in mind that other jurisdictions, such as California, have lower limits for the maximum amount of lead that you can have in your product. If you have a perovskite solar cell on either glass or plastic substrates, you would exceed this limit. And also the lead in perovskites is easily accessible. They can be easily dissolved into water, and the lead is bioaccumulative, so it can accumulate up the food chain, and by the time it reaches humans, it can be in quite dangerous levels. So we need to find alternatives, lead-free alternatives to the perovskites, which can replicate its exceptionally good optoelectronic properties. And the key enabling factor for the perovskites is its defect tolerance, which means that you can have lots of defects, you can grow at low temperatures, have lots of defects, but still have low non-rate of recombination rates. And that can be rationalized based off the electronic structure. So if you have a traditional material like silicon, in silicon, you form a bonding orbital in the valence band and an anti-bonding orbital in the conduction band. So you end up with the original atomic hybrid orbitals being close to the middle of the band gap. So when you break bonds by having vacancies, for example, the dangling bonds will be at energy states close to the original atomic orbitals. And that means you'll end up with deep defect states, which are very harmful and to the recombination process. So you have lots of irreversible losses in energy because of these defect states. And the only way to get around that is to not have the defect state in the first place. So you have to process these materials very carefully and have minimize the densities of these defects. By contrast with the perovskites, we have a very different electronic structure. We have s orbitals from the lead, which hybridize with the anion p orbitals to form this purple pair of bonding and anti-bonding orbital states. And we also have these empty p orbitals from the lead, which can hybridize with the anion p orbitals to also form this anti-bonding states in the valence bands and bonding state in the valence band and anti-bonding state in the conduction bands. And with this very different electronic structure, our atomic orbitals are now close to the bands rather than in the middle of the band gap. So if we do have defect states within the band gap, they're much more likely to be shallow rather than deep. And these shallow defect states are much less harmful, and we can still achieve low non-radiative recombination rates, even if we have them present in high densities. So we wanted to find materials that can replicate this perovskite electronic structure. And we hypothesized that we could do this with materials with a significant fraction of these s orbitals in the upper valence bands. So we looked towards materials based off partially oxidized p block cations, and that includes bismuth. So bismuth forms a stable 3+ oxidation state, and it then has the same electronic configuration as the lead does. So maybe these materials could replicate some of the important features of the perovskites. And the good thing about bismuth is that they're non-toxic. So bismuth is the green material in poisonous corridor in the periodic table. So on the left of bismuth, we have mercury, thallium, lead, which are the toxic elements. On the right, we have polonium, actinium, radon, which are the radioactive elements. But surprisingly, bismuth is neither toxic nor radioactive, and you would use bismuth-based materials in over-the-counter stomach medicine, for example. And also the abundance of bismuth is an order of magnitude larger than the abundance of tellurium. And tellurium was already used commercially in solar cells. So the abundance of bismuth is sufficient for commercialization in solar cells. So the first bismuth-based material I want to talk about is cesium silver bismuth bromide double perovskites. And the advantage of these double perovskites is that they preserve the perovskite crystal structure. So we have a look at the lead-based perovskites here. If you sum up the charges of two neighboring lead-halide octahedra, if you sum up the cation charges, you get +4. So if you replace both of those with bismuth, then you get +6. And in order to preserve charge neutrality, you cannot form a perovskite crystal structure anymore. So to overcome that, what you could do is replace one of these cations with bismuth 3+, and replace the other cation with a monovalent cation such as silver. And that's what a double perovskite is. You have alternating bismuth halide and silver halide octahedra. So you maintain this 3D symmetric perovskite crystal structure in these materials. And you get rid of the lead and replace it with silver and bismuth instead. And last time, in the previous LCN seminar, I showed that these double perovskites have very long charge carrier lifetimes, exceeding a microsecond. But the problem with these materials is that their band gaps are actually very wide, and they're too wide for even harvesting indoor light. And you can see here that in this external quantum efficiency spectrum that we're not absorbing the near infrared, and that's a problem if you're wanting to use this for outdoor solar cells, because a lot of the irradiance from the sun is in the infrared part of the spectrum. So the question is, can we lower the band gap of these double perovskites? And in particular, can we do that using antimony alloying? There's some quite promising results in the literature which show that if you add some antimony, you can reduce the band gap. But the question is, how much can you reduce the band gap by? And there's two issues. First of all, people previously were not able to completely alloy antimony into the system, so there's a limit that people were able to achieve in the past. And also the band gap of cesium silver antimony bromide is actually also quite wide. So there's a question of how much of a reduction in the band gap you could really achieve through antimony alloying. So I worked with one of my PhD students, and we developed a solution-based method which allowed us to tune the composition over the entire range from pure antimony to pure bismuth by controlling the temperature at which we dissolve the precursors in the DMSO solvents. And what you can see here from these photographs is that actually the middle composition, the alloys, have a smaller band gap than the N, have a darker color than the N compounds, which suggests that maybe these alloys have a smaller band gap. We checked the composition using Rutherford backscattering spectrometry, and we found that the bulk ratio of antimony to bismuth was the same as that in the precursor solutions. And we also verified that all of these compounds were phase pure. So in all cases, in all these alloys, we have phase pure double perovskites. So we then looked at the band gap, and we did that using photothermal deflection spectroscopy measurements, which allows us to have much better sensitivity in the near bandage region. So we make a tout plot, use the exponent with 0.5 because these materials have an indirect band gap. And what we saw that was really interesting is that the mixed alloys have a much smaller band gap. And that's consistent with what we saw visually in these films. And you can see here that if we were limited to only the band gaps between the pure compounds, then we only have quite a small reduction in the band from about 2.25 eV to 2.18 eV. But because of this rather unusual band gap Boeing effect, we could decrease the band gap by quite a significant amount that you can see here. And I also just wanted to point out that the change in the lattice parameter is very small in these alloys because we have the same space group, same cubic space group for both of the N compounds. So my collaborator Aaron, David, and the student Sean Kavana, they did some calculations to help us to understand what was causing the significant band gap Boeing. And you can see from these electronic structure calculations that we have a significantly indirect band gap. And what they did was they calculated the band alignment between the pure alloys. And what you can see here is that we have this type 2 band alignment. And what we propose is happening is that when we make the alloy, so if we start with pure bismuth and we add in some antimony, what we think is happening is that the electron wave function will want to spend more time in the lower energy site. So the electron wave function will have a larger amplitude around the bismuth in the conduction band, and the Hoye wave function will have a larger amplitude also in the lower energy site. And in the case of holes, that would be the antimony sites. So instead of having a linear variation in the band gap, we think that the conduction band would take on more of a bismuth character, whereas the whereas the valence band would take on more of an antimony character, and therefore you have a band gap in between these two extremes. So this could allow you to have a smaller band gap for the alloys than for either of the N compounds. So here we have the standard equation for the band gap of mixed alloys, and we have this B parameter here, which is the Boeing parameter. So the classical case is Vega's law, which is if you have an alloy, then you just have a linear variation in the band gap, and that will happen if you have B is equal to 0. In real materials, that's usually quite rare. So usually B does not equal 0, but it's usually some small value. So you then end up with some Boeing in the band gap variation with composition. But what could happen is that if the Boeing parameter is very large, if you have a very large Boeing parameter, then you could end up with a significant quadratic character in your band gap variation with composition, and then your mixed alloys will have a smaller band gap than either of the pure N compounds. And this can happen for a variety of different reasons. You could have structural effects. You could have, if you have a large difference in lattice parameter in your different N compounds. If you have cations with significantly different sizes, then you can have local size mismatch effects, or you can have chemical effects. So remember earlier I showed you that the lattice parameter didn't change very much. So we don't think it's due to structural effects, and bismuth and antimony have very similar ionic radii. So we don't think it's due to local size mismatch. But we do know that these materials have a type 2 band alignment. So we do think it could be due to these chemical effects where we have a non-linear mixing of the orbitals in our alloys. And we did some photoemission spectroscopy measurements to measure the band positions of these alloys. And if you just look at the pure antimony and the pure bismuth, what you can see is that we actually do have this type 2 band alignment. And what you can also see is that the alloys have a conduction band character very similar to that of the pure bismuth, and the valence band is somewhere in between the antimony and the bismuth. So this agrees with what we predicted based on the calculations. So to summarize part one, we were able to achieve phase pure double perovskites. We were able to alloy antimony over the entire composition range through solution processing, and we found that the mixed alloys of these compounds have lower band gaps than the pure compounds. First of all, due to the type 2 band alignment between these N compounds, and secondly, because of the nonlinear mixing between the atomic orbitals. And that happens because the antimony and bismuth have very similar chemical properties. And we think that this can be generalized. People have also found this effect with the lead-tin perovskite alloys. And we think that if you can look at other double perovskite systems and look for these features to find alloys which could have a smaller band gap than either of the endpoints. And that, I think, is very important to lower the band gaps so that they're more suitable for light harvesting applications. So now I want to go to the second part, which is moving on to bismuth oxyiodide and looking at their applications for indoor solar cells. So here's the structure of bismuth oxyiodide, and this is not a material you had thought about if you were just looking for lead-free perovskites. It doesn't have a perovskite crystal structure, and it's also not chemically analogous to the perovskites. But the reason why we thought about it is because we believe that bismuth-based compounds can replicate this antibonding to antibonding state transition across the band gap, which we think is really key for defect tolerance. So we grew this material by chemical vapor deposition using bismuth iodide plus oxygen gas as our precursors. And we found that these materials were stable in air. We tested them for 197 days in ambient air. We found the phase remained exactly the same. And this is 2 orders of magnitude better than methammonium lead iodide perovskites. I'm probably running short on time, so I won't go into this into too much detail. But we had some calculations which show that this material is defect tolerant because the low formation energy defects are the most common ones in these materials. And what we found was that the transition levels, the levels at which you have a change in the slope, either did not form within the band gap or were very shallow. So this agrees with our hypothesis that this material would tolerate these vacancy and anti-site defects by having shallow transition levels rather than deep defect states. And we also have some experiments to confirm this experimentally. And this was a work that was published earlier last year by one of my students, where we showed that the electronic structure was robust against percent levels of iodine and bismuth vacancies. And also the lifetime didn't change either when we have percent levels of these defects. So over here you can see the device structure that we used, that we developed for this material. This was the first all-inorganic device structure for bismuth oxyiodide. And here we use nickel oxide as a whole transport layer and zinc oxide as the electron transport layer. And the green curve that you see here is the external quantum efficiency spectrum. And the band gap with this material is 1.9 eV. So that's too wide for outdoor light harvesting. So there's all this infrared light from the sun, which won't get absorbed. But if you look at the indoor light spectrum, so for white light LEDs or for fluorescent lights, the spectrum is much narrower and is confined mostly over the visible wavelength range. And for harvesting indoor light, actually the optimum band gap is 1.9 electron volts, and that's a band gap that bismuth oxyiodide has. So we tested these photovoltaics, so under one sun illumination, the efficiency was only about 1%. So that's not the best device we ever made. The best device we've made is 2%, and that's currently the record for bismuth oxyiodide. But still, it's not high enough for outdoor applications because of its wide band gap. But we took the same device and we put it under indoor lighting, and then straight away we got a significant improvement in the efficiency up to 4.4% under fluorescent lighting. And that's significant because for indoor photovoltaics, the current commercial technology is amorphous silicon, and the efficiency of amorphous silicon is 4.4% to 9.2%. So with our first demonstration using devices which weren't the very best we ever made, we could already enter into the range of efficiencies demonstrated with the current commercial technology. And we also demonstrated that these devices could power inverters. So this is a carbon nanotube inverter that my collaborators made. And we showed that we could use the bismuth oxyide solar cells to power them. You can see that if you put a high input, you get a low output. If you have a low input, you get a high output. And that is exactly what a NOT gate is supposed to do. And we also tested these devices under different illuminances. And here you can see that even though we're varying the illuminance from 500 to 1,000 lux, there isn't much of a change in these voltage transfer curves for the inverters. So this has practical importance as well, because if you're wearing these devices in your clothing or in your smartwatch, if you walk to different parts of the room, you get different illuminance levels, but this won't affect the logical operation of your devices, which is really an important practical advantage. So now the question is, what's the efficiency potential for bismuth oxyiodide? Where can we go in the future? So we measured the absorption coefficient of this material, and we use this to calculate what would happen if all the light absorbed gets converted to carriers, and if all of these carriers were extracted from the device. And we found that in that case, the efficiency would be 44%. And that's the best case scenario, and it's a lot higher than the current efficiency of amorphous silicon. So this material has a lot of potential, and especially since the material is stable and has potential to last for 20 years if you make it in an encapsulated device and commercialize it. But we also looked at the potential of a wide range of other perovskite-inspired materials based on bismuth and antimony. And we found that a lot of these materials have a lot of potential as well. For example, you have these rutherfites, which can reach up to 60% efficiency under indoor lighting. And that's important because this was the first demonstration of the potential of perovskite-inspired materials for indoor PV. And what we show is that although up to now, most people have looked at these lead-free materials as alternatives to the perovskites for outdoor applications, they actually have a lot more potential for indoor PV applications where they'll be especially important for powering IoT electronics. So to summarize part 2, what we've shown is that bismuth oxyiodide is air stable and it has the ideal band gap for indoor PV. We calculated that the efficiencies can go up to 44% in the best case scenario for a fully optimized device. And we showed both computationally and experimentally that this material can tolerate defects. In our first demonstration for indoor PV, we got an efficiency of 4.4%, and that is within range of the current commercial technology, the amorphous silicon, and is already sufficient to power inverters. So finally, I'd like to thank again the people who worked with me on these projects. I'd also like to thank the Royal Academy of Engineering again. And here we have a overall summary of the 3 of the papers that I talked about today. So, and also thank you all very much for listening. I'd be very happy to take questions.
Robert, thank you very much indeed. That was a fantastic talk, and it really shows the strength of really solid material science in pushing forward a technology, a completely new technology. And I think this indoor PV thing is really, really exciting. And so I'm going to ask